Hello everyone, in this video we are going to look at examples of free energy under thermochemistry. The first example here says predict the sign of entropy change for each process. Here we have gas, H2O gas going into liquid water. So the entropy change for this is going to be negative, because gas has a greater entropy than liquid. So for solid carbon that does sublime, delta S is going to be positive because solid has a lower entropy than gas. For N2O gas going into 2 nitrogen and oxygen, in this case we are going to use the moles of products and reactants that are formed. In the product here, we have 2 nitrogen and 1 of oxygen, giving 3 moles in total. But for the reactant, we just have only 2 of N2O, giving 2 moles. So the product has more moles than the reactant. So we're going to say delta S is positive because there is increase in the number of moles of the gases. For the fourth one, we are having gas going into solid. So our delta S is going to be negative because of the gas has a greater entropy than solid. For the last one, our delta S is going to be positive because solid has a lower entropy. Let's go to the next example. Given this equation and with heat of reaction to be negative 2044, calculate the entropy change in the surrounding when this reaction occurs at 25 degrees C. Determine the sign of entropy change for the system and determine the entropy change for the universe. And is the reaction spontaneous? So to calculate the entropy change for the surrounding, our delta S surrounding is given as negative heat of reaction over the temperature. So in this case, we're going to have negative of negative 2044 kilojoule over our T. We know our T is 25 degrees C. We're going to convert it to Kelvin. So that gives us 298 K. So we're going to plug in that into here as 298 K. So this is going to give us positive 6.86 kilojoule per Kelvin, or we can say positive 6.8 times 10 to 3 joules per K. So that is the delta S for the surrounding. So for the second part, which says we should determine the sign of the entropy change for the system. So what we're going to do is we're going to calculate the number of moles of all the reactants and the products. For the reactants, we have 1 plus 5, which is 6. And for the products, we have 3 plus 4, which is 7. So we're going to say the reactants are 6 moles. And the products, the moles of the gas. For the reactants, we have 6 moles total. And for the products, we have 7 moles in total. So we can see that there is an increase in the number of moles of the gas from reactants to from the reactants to product. So we can say our delta S in this case is going to be positive. Determine the entropy change for the universe. So that is what the C part says. So what we do is the universe is going to be the sum of the entropy change for the system and the surrounding. For the system, which we have here, is positive, and for the surrounding we have positive. Both of them is going to give us the entropy change for the surrounding is going to be positive, and whenever it is positive, it means it is spontaneous. Next example, for the reaction, calculate delta G at 25 degrees C and determine if the reaction is spontaneous. So again, we have this relationship for delta G given as this, and our reaction is going to be at 25, so we need to convert our 25 to K, which is going to give us 298 K. So that is our T here. So our H has been given to be 95.7, and our delta S entropy change has been given to be that. So what we need to do is to plug in these values into this equation. So it's going to give us 95.7. We need to convert that to joules because we have joules here. So that is going to be 10 to the power 3 minus our T is 298 times positive 142.2 joule. So when we plug that into the calculator, it's going to give us 95.7 times 10 to the 3 minus 42.4 times 10 into 3 joules. Alright. So we're gonna have the final answer from our calculator gives us positive 53.3 times 10 to 3 joules. Because we have this positive sign here, it means our reaction is not spontaneous. Right. Positive means non-spontaneous. Positive delta G. The next example we have here says calculate delta S entropy of reaction for this reaction. So what we need to use for this is the relationship that is written here, and the standard entropy for our reactants and products has been given in this table. This will be given for any problems. So what we just need to do is to plug in these values into our expression that we have written. The N that we have here represents the number of moles of our reactants and products respectively. So we now say our delta S of reaction is going to be, this is a product. We have 4 moles of NO. So we have 4 into the entropy of NO plus we have 6 of water, entropy of water. These are our products, and for the reactants we have 4 of ammonia, 4 of the entropy for ammonia plus 5 of the entropy of oxygen gas. So we plug in all these values here. We have 4 for NO, which is 210.8, which is this here, plus 6 into the water. Our water is 188.8 minus 4 into our ammonia, which is 192.8 plus 5 into our oxygen, which is 205.2. Right. When we plug in all this into the calculator, we're going to have everything here to be 1976.0, and everything here is going to give us 1797.2. We put everything together and it's going to give us 178.82. Okay. So that is our change in entropy of reaction for the given reaction in this problem. The next example says calculate the G of reaction at 25 degrees for this reaction. In this problem, our heat of reaction is not given, unlike the previous problem, and delta S of reaction is not given. However, this table has been given to us, so we find it the same way we have been doing before. So we know our T is at 25, so that is going to give us 298 K when we convert that. So for our entropy, for our heat of reaction, is going to be the product minus the reaction. So our product here is SO3. So we have 1 of delta HF, which is given for SO3, minus we have oxygen and SO2. 1 of delta HF of SO2 plus half of delta HF of oxygen. Alright, so we plug this together. So this is what we're going to use now for this first one. So we're going to have negative, this is SO3, negative 395.7, right, minus SO2 is going to be negative 296.8 plus half of oxygen, which is 0. So this is going to go away. So we're going to have negative 395.7 plus 296.8, and that is going to give us negative 98.9 kilojoule. That is our delta heat of reaction. So what we need we already know this, we need to find the entropy. So in likewise, we're going to find the entropy of reaction the same way. is going to be the product minus reactant as usual. So for SO3, which is still warm, for the entropy is going to be 256.8, right, minus the products, which we have 248 for SO2, 248.2 plus half of oxygen. Our oxygen here is 205.2. This as our oxygen. So when we plug everything here together, and that is going to give us 256.8 minus 248.2 plus 102.6. And when we plug this into the calculator, it's going to give us negative 94 kilojoules. So that is our delta S. So we're not going to plug everything, put everything together to give us our delta G of reaction, right, which is going to be negative 98.9 times 10 to 3 joules minus our T is 298 into negative 94 times 10 to 3 joules. Right. When we plug all this together, we're going to have the total to be negative 70.9 times 10 to 3 joules. Alright, so because our delta G here is negative, it means that this reaction is going to be spontaneous. Delta G is negative. So the next example we want to take a look at is calculating delta G from standard free energies of formation. So this is also similar to what we have been doing before. It's going to be the formation of all the delta G of the product minus the reactant. So the standard free energy will be given, which is already in this table before. So for this reaction, we have 3 products and 2 reactants. So we're going to do it for everyone. So for the G of reaction, so for the product, we're going to have, we have 1 mole of carbon, and our CO2, we have 1 mole of CO2, which is 394.4. So we say our product is negative 394.4 plus we have 2 of water, so 2 of H2O, which we have here, negative 228.6 plus we have 4 of ozone, so which is going to be 4 into 163.2. We have everything like that, minus the product that we have is 1 mole of CH4, and our CH4 is negative 50.5 plus we have 8 moles of oxygen, and our oxygen is 0, right? So everything here is going to go away because it is 0. So whatever we're going to have, what is left, if you plug all this into our calculator, it's going to give us 198.8 kilojoule, right, minus negative 50.5. So when we plug everything together, this is going to give us 198.8 kilojoule plus 50.5 kilojoule, and this is going to give us 148.3. Right, so we want to take another example, calculate the equilibrium constant for the reaction at 298 K. So we don't need any conversion for this because this is already in Kelvin. So we need to remember that to solve a problem like this, we're going to say our delta G of reaction is going to be negative RT ln K. Alright, so we are calculating the equilibrium constant, which is our K, right? So we rearrange this equation, which is going to give us ln K equals to negative delta G of reaction over RT. However, we know this is a gas constant, our R, and the T is the temperature given. We need to be able to calculate our delta G of reaction before we can find our K, ln K. So we use this equation here to find our delta G of reaction, so which is the delta G of formation of products minus reactant. So we already have this table provided for us, so we just plug in those values. We have only one product and one reactant here, makes life easier for us. So we have 2 moles of NO2, so and our NO2 is 51.3, and minus we have 1 mole of N2O4, which is still just 99.8 kilojoule. So when we plug this into our calculator, we have 2.8 kilojoule, or we can say 2.8 times 10 to 3 joules, whichever one we want to use. So we already find our delta G of reaction from here. So what we do is we just plug it into this equation, and it's going to give us negative 2.8 times 10 to 3 over R, which is our gas constant, and that is going to be 8.314 joule per mole Kelvin times 298 K, which has been given to us. When we plug this into calculator, it gives us negative 1.13. So the next thing we do is we are actually looking for K, not ln K. Ln K is negative 1.13. So what we need to do is to go into our calculator so that we can find our K. We now find the exponent of 1.13, and that will give us 0.32. That gives us the value of our equilibrium constant. So this is how we approach and solve problems on free energy. I hope these problems can help us to solve as many problems as we can. Thanks for watching.